Welcome back to MATA02, the magic of numbers. In this half of lecture, we're going to be talking about divisibility and the Euclidean algorithm. So this is lecture 2C. And let's get started by talking about some sort of abstract definitions and examples. What does it mean for something to be divisible? Well, a positive integer a is divisible by another positive integer b if a divided by b is equal to, well, the fraction a over b, but that fraction is actually a positive integer. It's a whole number. Another way of thinking about it is it's divisible if a divided by b has no remainder. Alternately, Alternately, another way of thinking about it is there exists a positive integer c such that b times c is equal to a. Let's give a couple examples of this. You guys have seen divisible things before, but let's just make sure we're all on the same page. So, well, 24 divided by 6 is equal to 24 over 6, which is equal to 4. Equivalently, 4 times 6 is equal to 24. Equal to 24. And so therefore, this is divisible. So 24 is divisible by 6. Let's do another one. So 17 divided by 1 is equal to 17 over 1, which is equal to 17. And we also know that 17 times 1 is equal to 17. And so this is also divisible. One thing you should pretty quickly notice, if you didn't know it already, everything is divisible by 1. Or every positive integer is divisible by 1. And let's give one more example. So let's have 17 divided by 2. 17 divided by 2 is 17 over 2, which is equal to 8 1/2, or 8 remainder 1. So another way of saying this is that 8 times 2 plus 1 is equal to 17. So note this is not divisible. Okay? And when we say divisible, we really just mean that you can divide up 17 apples equally among 2 people, which you can't, and so it's not divisible. Let's do some sanity checking, make sure you guys are all on the same page as me. Is 52 divisible by, let me reset my chat. Is 52 divisible by 13? Yes? No? Maybe? None of the above? Okay, so a lot of people are saying no. And, well, let's see what happens. So it turns out that when you try to divide 51 into 13, you get, well, let's do this as long division. 51 divided by 13. Well, let's see, what can you multiply this by? Multiply this by 3, 39, 12. So it's 3 remainder 12. So yes, this is not divisible. So the answer is indeed B. What about by 17? And let me reset. So is 51 divisible by 17? Okay, yeah, so people are answering yes, and that is because 51 is equal to 17 times 3. Okay, so it looks like we're all on the same page. Excuse me. So one of the things you guys probably learned in school is this thing called long division. So now one of the things that you might notice is that division seems harder than it's the opposite of multiplication, but it's somehow harder than multiplication and involves a lot of multiplications. So what do we mean by that? Well, as an example, let's say that I wanted to divide some complicated number, let's say 5, 4, 3, 2, 1 by 12. Well, what is that? Well, if you're doing long division, well, the first thing to do is you put a 4 here because 4 times 12 is 48, which is the largest multiple of 12, smaller than 54. You subtract that out, you end up with 6, you put the 3 there, and then you put a 5 here, since 60 is the largest multiple of 12, that is smaller than 63. So then you get 32, you repeat that, so you get a 2 there, 24, 81. You get a 6 there, so that's 72, 9, remainder 9. And you notice we had to do a lot of multiplications there to get that, whereas if you just wanted to multiply through, it would in some ways be easier somehow. And so sometimes reversing operations is harder. Well, now let's go back to a history of operations. So we've been talking about when different operations were invented, and I didn't really talk about when division was invented, right? So, well, let's remind ourselves when things were invented. Negative numbers were invented around 200 BC to 200 AD. Multiplication was invented by around 4000 BC by the Babylonians. But the Babylonians didn't actually have full division. They hadn't completely invented division, though they did have something that was, they did have division by, they did have a form of division that was a little bit more complicated. Or, sorry, not more complicated, but it wasn't as powerful. So what they did is, you'll recognize that when you divide by something like, so let's say they're working in decimals. So the Babylonians actually worked in base 60, but we're going to work in decimals since that's a bit easier for us. So say that we know that 1 over 5 is equal to 0.2. So if we're going to work in decimal, well, then what you can do is, well then, you know that say 11 divided by 5 is equal to 11 times 0.2, which is equal to 2.2. So this is one way of doing division, but it only works if you already know the inverse of it and can write it down as a decimal. So this sort of works, but it isn't quite as powerful as like long division. Which of course brings us to our history question. So let me reset. So when was direct division invented? Was it before 1000 BCE? Was it between 1000 BCE to 1000 CE? Was it between 1000 and 1500, between 1500 and 1800, or after 1800 in the current era? Okay, so we have a pretty good mix of like different things. I already sort of hinted that the ancient Babylonians didn't really invent direct division, so maybe it was somewhat later than that. But the question is how much later? It looks like a lot of people are guessing between 1000 and 1500 CE, which actually isn't a terrible guess. In fact, people were reinventing this a number of times, but in this case, that is not quite right. So it turns out the ancient Egyptians, so this is around 1500 BCE in Egypt. The ancient Egyptians had these papyruses that they put math problems on. So people were doing math problems, including direct division back in 1500 BCE in Egypt. So this was still ages and ages ago. So it took a lot longer than multiplication, but it didn't. So it took like an extra 2,000, 3,000 years after multiplication. But you have to remember the ancient Babylonians were 6,000 years ago. So even if you take another couple thousand years after that, it was still 1,500 years BCE before the current era. So they had a division for a while. But now let's ask another question. When was modern long division invented? So the modern technique we use for long division, the one I showed you a little bit ago. Okay, so let's see. So a lot of people are saying this was in the after the 1800s. So that's the guess. We have a couple people who are guessing a little bit before then. Well, it turns out that modern long division was invented by this guy, Henry Briggs, who lived between 1560 and 1630. He was a professor at Oxford as well as at other universities, but the person who invented the modern formulation of long division. So when we write out this thing by 5 or whatever, when we write out modern long division, that was invented by Henry Briggs, and that was a professor at a university that's still around today. So you can still go over to Oxford, it still exists, and the professor there invented the modern formulation of long division. Though, of course, like we've had direct division, so like other ways of writing it since antiquity. Okay, so that's a nice little history interlude. So let's now get back to trying to really properly understand what division does and what it means. So what numbers are divisible by 4? So there are a couple ways of doing this. One is we can just list out every single number and test them. So now, if you didn't know anything about math, and I ask you this I ask you this question, what numbers are divisible by 4? This might be what you'd have to do, because you don't have any general rules for it yet. So let's start. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now, of course, you can't list out every number since there are an infinite number of them, but you can test a few and see if you see a pattern. So, is 1 divisible by 4? No, of course not. Is 2 divisible by 4? No. 3? Nope. 4 is, though. So 4 is divisible by 4. 5 is not. 6 not. 7 not. 8 is. 9, 10, and 11 aren't. But 12 is. 13, 14, 15 aren't. 16 is. 17, 18, 19 aren't. I wrote that wrong. But 20 is. 21, 22, and 23 aren't, but 24 is. Yes, exactly, Maria. So, you notice a pattern, right? So all the multiples of 4. Exactly. So all the multiples of 4 are divisible by 4. So solution 2, once we know the pattern, we can recognize that's just all multiples of 4, which we can also prove. So now, when you see the pattern, that doesn't necessarily mean it's always true. Like, there are an infinite number of numbers, and so you can't really test all of them. But you can ask yourself, can I reason about whether or not this is true? So, how do you reason about whether or not it's all multiples of 4? Well, you can think about it. So, in order to show that it's all the multiples of 4, you need to show that first, if it's a multiple of 4, then it's divisible, and then you need to show that if it's divisible, then it's also a multiple of 4. So let's think about that a little bit. Is this because multiplication is the opposite of division? Yes. Well, this is basically the reason why multiplication is just because they're opposites. Let's formalize that. So if A is divisible by 4, then we know that A over 4 is equal to B, where B is another integer, right? So that's sort of the definition of divisible by 4. But if you multiply both sides by 4, but reversing the operation, like you were suggesting, then that means that A is equal to 4B, which is exactly what we were saying, that A is a multiple of 4. On the other hand, if A is a multiple of 4, so if A is equal to 4B to start off with, then we can divide both sides by 4. Then A over 4 is equal to B, so A is divisible by 4. So therefore, the numbers divisible by 4 are just all the multiples of 4. Okay, and so that's another simple proof. So we've now written this out as a proof, and yes, and we sort of had the idea for what we needed to prove by just listing out numbers and seeing this pattern. Now, there will be some exercises later where I might have you guys do this, but they're a lot easier in person, so for now I'm just going to do it this way. Okay, so that's easy, and it turns out that the same kind of reasoning works for basically all the natural numbers. So the numbers divisible by 5 are exactly the multiples of 5. Numbers divisible by 6 are the multiples of 6. Okay, so that's easy enough. Like, it's sort of obvious, right? Because multiplication is the opposite of division. But now let's ask a harder question. What numbers are divisible by both 4 and 6? And now this gets a little trickier, right? So the first thing you'll notice is, well, what is a number? What is the easiest number you can think of that's divisible by both 4 and 6? Okay, so we have some people who are answering 12 and some people answering 24. But in some ways, so there are different ways you can think about that. I'm going to claim that 24 is the easiest number to think of as divisible by both of them, because you know that's a multiple of both, since you're literally seeing it as a multiple of both in this particular case. Sorry. And then obviously, any multiple of 24 is also divisible by, is divisible for the following reason, divisible. So if a is equal to 24b, then a over 4 is equal to 24b over 4, which is equal to 6b, so this is an integer, since b was an integer. So a is divisible by 4, so a is divisible by 4, and if a is equal to 24b, then a over 6 is equal to 24 over 6b is equal to 4b, which is also an integer. So a is divisible by 6. Plus, multiples of 24 are divisible by both 4 and 6. Okay, so that's the same sort of reasoning, and we can just show that any multiple of 24 is divisible by both 4 and 6 for the following reason. Now, well, I was about to ask, are any other numbers divisible by 4 and 6? But a bunch of you had already given 12, so I'm not going to bother asking that. And the one way, so there are a couple different ways of figuring this out. What are these other numbers divisible by 4 and 6? One is you could list out all the numbers again and divide it by both 4 and 6, but that would take a long time. Another way you can do this is you can list out numbers divisible by 4, list out numbers divisible by 6, and look for any overlapping numbers. So let's say 4b, so all the multiples of 4, well, what is that? 4, 8, 12, 16, 20, 24, 28, 32, 36, and let's say 6b, 6, 12, 18, 24, 30, 36, 42, and so on. And then, well, which numbers are divisible by both? Well, we have 12 here, we have 24 here, and we have 36 here. So 12, 24, and 36 are divisible by both. So given that pattern, you might have, and given like what we've seen about other things that are divisibility, you might have a guess. And the guess that we have is that hypothesis. All multiples of 12 are divisible by both 4 and 6. And we can prove this. So let's go ahead and prove it. So the claim is that the set of all numbers divisible by both 4 and 6 is exactly all multiples of 12. So there are two steps to this proof. The first one is to show that all multiples of 12 are divisible by 4 and 6, and the second one is to show that all numbers divisible by 4 and 6 are multiples of 12. So let's start with the first step, which is pretty easy. It's the same sort of reasoning as before. So if a is equal to 12b, where those are integers, so we're only going to work with integers for this section of class. Well, that's not quite true, but let me say that explicitly. Where a and b integers, then we know that a over 4 is equal to 3b, and a over 6 is equal to 2b, so a is divisible by both 4 and 6. Okay, the second part is a little bit harder, but when you say that a is not divisible by, so we're going to show that if something is not divisible by 12, then it can't be a multiple of 12. So we're going to show the opposite direction. So suppose a is equal to 12b plus r, where r is one of 1, 2 through 11. Why did we do that? Because we're basically saying that there is a non-zero remainder. So we're basically saying that when a is divided by 12, you get a non-zero remainder, which we can write out in this way. Well, then what we know is that a over 4 is equal to 3b plus r over 4, and a over 6 is equal to 2b plus r over 6. So in order to be divisible by both 4 and 6, r over 4 and r over 6 must both be integers. But we can just check for each of our 11 integers. So no integer between 1 and 11 works. So a cannot be divisible by both. Sorry, I ran out a bit out of space there. But so with this proof, you can show that the set of numbers divisible by both 4 and 6 is exactly all multiples of 12. And so we did this specifically for these two numbers, but you can try to come up with a general rule. And there is a general rule here, which is the rule of least common multiples. So given the problem is given two numbers, a and b, which are both positive integers, what numbers are divisible by both a and b? Well, the solution is the least common multiple, defined as the smallest number that's the multiple of both a and b. So, for example, the least common multiple of 6 and 9, well, what is that? Well, let's see, 6, 9, oh, sorry, I need multiples of 6 and multiples of 9 to figure this out. 6, 12, 18, 24, and 9, 18, okay, we already found one. So 18, that's equal to 18. And so the number is divisible by 6 and 9 are the multiples of 18. Okay, and let's do one more example. So let's say the least common multiple of 15 and 21. Well, what's that equal to? Well, 15, 30, 45, 60, 75, 90. Well, we write out a few of them, and then we see if we have any common ones. So let's see, 21, 42, 63, 84, 105. We don't have any yet, but it turns out that if we keep on going a little bit further, we get 105 on both of these. So that is the least common multiple. So the numbers divisible by both 15 and 21 are the multiples of 105. And you can prove this in the same general way. I'm not going to expect you to be able to do this, but it's useful for you to hear it and be able to follow it. So earlier we proved that the set of numbers divisible by 4 and 6 is exactly the multiples of 12. We can prove that the set of numbers divisible by a and b is exactly the multiples of the lowest common multiple of a and b using the same kinds of ideas. So first we'll prove that any multiple of the lowest common multiple of a and b is divisible by both a and b. And then we prove that if a number is not a multiple of the least common multiple, then it will have a remainder when divided by one of a or b. So how do we do that? Well, if you have a number that is c times the least common multiple of a or b, well, and then you divide it by a, that's going to be c times the least common multiple of a or b divided by a. But of course, this thing here is an integer, because by definition, the least common multiple is a multiple. Least common multiple of ab is a multiple of a. And the same is true for b. And so if you write that, so the same is true for b, and therefore the least common multiple is divisible. Any multiple of the least common multiple is divisible by both a and b. Well, next we need to prove that if a number is not a multiple of the least common multiple, then it will have a remainder when it's divided by either one of a or b. So if you write out a number like that, that might be c times least common multiple of ab plus r, where r is, well, between 1 and the least common multiple. So note that this is divisible by a if r over a is an integer, and divisible by b if r over b is an integer. But if r is a multiple of both a and b, it cannot be smaller than the least common multiple of a and b. Okay, I'm going to take a breather there, and ask for any questions, because some of this was a little bit abstract and esoteric. The basic idea is we want to understand what is the set of things that divide multiple numbers, and the way you get that is by this least common multiple, and then you can actually prove that this is always true. Any questions? Okay, great. So let's now try it out. So I'm not going to make you try out the proof, but I am going to make you try out these least common multiples. So let's try it out. Let me reset my chat. So what is the set of numbers divisible by 14 and 21? You know, all the multiples of 14, all the multiples of 21, all the multiples of 28, all the multiples of 42, or none of the above? Okay, looks like we have a lot of people going for 42. Well, let's see. So 14, 28, 42, and we have 21, 42. So yes, the least common multiple of them is indeed 42. Okay, let's try another one. What's the least common multiple of numbers divisible by 2 and 10? Oh, I think we had a leftover D. I think that was from the previous one. Oh yeah, that changed. Okay. So most people here are saying all multiples of 10. It is, of course, true that all multiples of 20 would always be divisible, but it's not the entire set of numbers. And we can figure this out because, well, let's take a look. 2, 4, 6, 8, 10, and 10. Note that 10 is the least common multiple of 2 and 10. And so the answer here is actually B. Note that if one of the numbers is divisible by the other number, well, then that means that the least common multiple is just a bigger number. Okay, so now we have some way of figuring out these least common multiples, but the way we do it right now, we have to write out lists of the least common multiples of both numbers and then figure out the first time they overlap, which is kind of slow, especially when you have really big numbers. Can we find the least common multiple of A and B faster? Well, sometimes. So there are a number of different situations under which we might be able to. So sometimes the least common multiple of A and B is equal to AB. So let's always a possible guess. So sometimes, for example, least common multiple of 3 and 5 is 15, because 3, 6, 9, 12, 15, 5, 10, 15. Okay, and so we're going to try to spend some time to understand these sorts of special cases because we want to know the general case. And so sometimes it's useful to understand these easier cases first. So sometimes the least common multiple is just the product of the two. Sometimes the least common multiple of A and B is equal to A, where A is greater than B. Sometimes it's the bigger of the two numbers. We saw it a moment ago. So for example, the least common multiple of 2 and 8 is equal to 8. 2, 4, 6, 8, and just 8. Note that when A is greater than B, the least common multiple of A and B cannot be equal to B because the positive multiple of A can't be smaller than itself. So the least common multiple of two numbers can't be smaller than one of the numbers, right? So now, can we figure out when the other two cases are true? Well, I've already sort of given away one of the two cases. So sometimes the least common multiple of A and B is equal to the max of A and B. When is this true? Well, we can look at a couple examples. The least common multiple of 2 and 4 is equal to 4. Least common multiple of 2 and 6 is equal to 6. Least common multiple of 3 and 6 is also equal to 6. Least common multiple of 2 and 8 is equal to 8. Least common multiple of 4 and 8 is equal to 8. And the least common multiple of 8 and 8 is equal to 8. So, note, it always seems to happen when the bigger number is a multiple of the smaller. And this makes sense, right? Because if the least common multiple is the larger number, that means that the larger number is a multiple of the smaller number, and of course, the smallest multiple of a number is itself. But now, let's do a slightly harder one. which is the other case. When is the least common multiple of AB just the product of A and B, just A times B? So when is this true? So respond in chat with hypotheses. So I've listed out a bunch of numbers. So where I've listed out A and B, the product of the two, and the least common multiple of them. And I've also created this additional column, AB divided by the least common multiple, just as an additional piece of evidence to hopefully help you see patterns. So when is the least common multiple of A and B equal to AB? Or equal to A times B? Oh, what does the CM stand for? Wait, do I have a CM in here? Oh, the LCM, least common multiple. Yeah, so least common multiple. Yeah, thank you for asking me to clarify that. So LCM. Or the lowest common, or lowest. I think it's often referred to as lowest, so same thing, yeah. Oh, no, yeah, it's not 1 centimeter. Yes, I apologize for that confusion. I probably should not have put it in italics. I should have just put it in, yeah, so. So, okay, so we have one hypothesis. The least common multiple of AB is equal to AB when the LCM is 1. Okay, so the other hypothesis, when AB divided by the least common multiple of AB is equal to 1. So when the LCM is the product of the numbers, okay, yeah, so that's true, but that's in some ways not super interesting, right? Because if two numbers are the same, then when you divide one by the other, it's going to be equal to 1. Can you figure out anything directly from A and B? Okay, so we have someone guessing prime numbers, which we haven't invented in this class yet, but that certainly has something to do with this. Another person who's guessing is AB when A is an even number and B is an odd number. Is that true in every case here? But what about the case for 3 and 7? But yeah, but you're on the right track. So somehow it's a little bit hard to see, but when the least common multiple of AB is equal to AB, when there is no common, the biggest common divisor of the two of them is equal to 1, which we'll make formal in a moment. So you'll notice that there isn't so in this case, there isn't a number that divides into both 2 and 5 other than 1. Or in this case, 3 and 7, there isn't a number that divides into 3 and 7 other than 1. Whereas in this case of, say, like 9 and 15, the number 3 divides into both of them. And you know that number's there. And so this is actually one of the things I also wanted you to notice, which is there any relationship between the rightmost column and its relationship to A and B? And the answer is that this number in the rightmost column always is a divisor. So the numbers A and B are always divisible by this number in the rightmost column. So that's 14 and 21. And somehow these divisors really do encode when the least common multiples. Did something just happen? Okay, good. Nothing happened. Yeah. So the least common multiples really are encoded in these greatest common divisors. So what do we mean by that? Let GCD, I remember to put this not in italics, of A and B, the greatest common divisor, be the largest number dividing both A and B. So as an example, the greatest common divisor of 4 and 6 is the biggest number that divides both of them, which is equal to 2. The greatest common divisor of 9 and 33 is equal to 3. The greatest common divisor of 5 and 10 is equal to 5. So sometimes it's one of the numbers themselves. The greatest common divisor of 1 and 5 is equal to 1. Now, here's an important theorem that I'm not going to prove yet, but which is super important, which is that for any two numbers A and B, AB is equal to, the product of the two numbers is equal to the product of the least common multiple times the greatest common divisor. So example, the greatest common divisor of 4 and 6 is equal to 2, and the least common multiple of 4 and 6 we already know to be 12. And you notice that 4 times 6 is equal to 2 times 12 because they're both equal to 24. Okay, but now, of course, I haven't really told you how to find the greatest common divisor. So, how do we find it? So, obviously, if we can find the greatest common divisor, then we can also find the least common multiple, and vice versa, just by dividing from the product. But now we have to ask if we can quickly find the greatest common divisor. And one solution is to write out all the divisors of both. So, for example, if I wanted to find the greatest common divisor of 9 and 12, well, what would I do? Well, divisors of 9, so let's write them all out. 1, 2, 3, 4, 5, 6, 7, 8, 9. So those divisors have to be one of those. 2 is not a divisor, because 9 divided by 2 is not an integer. 3 is, 4 is not, 5 is not, 6 is not, 7 is not, 8 is not. You can also write out the divisors of 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, let's see. So 1 is a divisor, 2 is a divisor because 12 divided by 2 is 6. 3 is a divisor because 12 divided by 3 is 4. And 4 is also a divisor. 5 is not, 6 is, 7, 8, 9, 10, and 11 are all not. Okay, but importantly, 3 is the greatest common divisor of both of these. So this is equal to 3. But unfortunately, this isn't really faster, right? So this is not much better than finding faster than finding the least common multiple directly. Right? Because we could have multiples of 9 and multiples of 12. So 9, 18, 27, 36, and 12, 24, 36. And that gets us the least common multiple really quickly. And then you know that, so then least common multiple of 9 and 12 is equal to 36. And we can also then solve for either one by just taking 9 times 12 is equal to 3 times 36. Okay, I did a bunch of different steps there. Is anyone confused? So basically what I'm saying is that doing this naive method isn't actually any faster than just finding it directly. But luckily there is a smarter method. So some of you, hopefully most of you, will have heard of Euclid, which is an ancient Greek mathematician, or group of mathematicians. It's hard to really know since it's so long ago, but a Greek mathematician who figured out a smarter method. So if you want to find the greatest common divisor of say 30 and 69. These are big numbers. It would take a while if I were to write them all out to figure out what the greatest common divisor is. But there's a trick we can use. So notice that if 30 divided by d and 69 divided by d are integers, then so is 30 divided by d plus 69 divided by d, right? Because you can think of this as two different numbers, say x and y. Well, if those are integers, then you know x plus y, x minus y, 2x plus y, x minus 3y, etc. are integers. Not necessarily might be negative, but we're going to ignore that for now. Okay? So we know this fact about them, and now notice 69 divided by 30 is equal to 2 remainder 9. So that's equivalent. We can say 69 is equal to 30 times 2 plus 9. So that implies that 69 minus 30 times 2 is equal to 9. But we know if we divide both sides by d now, 69 divided by d minus 30 divided by d times 2 is equal to 9 divided by d. But we know that this here is x and that's y. So we know that the left-hand side are integers. So we know that 9 over d is an integer. So d divides 9. Conversely, we can use the same sort of reasoning, and I'm not going to go through it in detail, but the same sort of reasoning to show the greatest common divisor of 9 and 30 also divides 69. So we know that the greatest common divisor of 30 and 69 is equal to the greatest common divisor of 9 and 30. But now this has made it simpler, right? Because now all of a sudden we're taking the greatest common divisor of two smaller numbers. So we can continue on. And, so now notice that 30 is equal to 3 times 9 plus 3. And 30 divided by 9 is equal to 3 remainder 3. So the greatest common divisor of 9 and 30 is equal to the greatest common divisor of 3 and 9, which is equal to 3, which implies that the greatest common divisor of 30 and 69 was equal to 3. Okay? And so we can codify all this in something called the Euclidean algorithm. So to find the greatest common divisor of a and b with b greater than a, the first thing you do is you divide a into b and let r be the remainder. If r equals to 0, we're done, and a divides b, and the greatest common divisor is just the bigger of the two. If r is not equal to 0, then we replace a and b with r and a and repeat the process. So what do we mean? As an example, the greatest common divisor of 24 and 1,000. How do we get this? Well, you just divide. 1,000 divided by 24 is equal to, well, that's 4, and that's 96. So that's 40, 41. So that's 24, 16, remainder 16. So this thing is equal to the greatest common divisor of 16 and 24. And if we keep on going, we'll find that that's equal to the greatest common divisor of 8 and 16, which is just then equal to 8. So let's have you all try it out. And that will... Hey, sir, your writing isn't aligning. Oh, wait a moment. Oh, yeah, sorry.
Is there something else I can help with?
Oh, no, stop talking, Siri. Yeah, it's just lag. Sorry about that. There's some amount of lag in my writing. Okay, hopefully that's all showing up. I'm not sure why I'm getting lag today, but let's have you all try it out. So what's the greatest common divisor of 24 and 1,234? So I am running out of time, so let me go ahead and start working this one out with y'all. So the first thing to notice is that, we have some people who are guessing 9,333. No, wait, sorry, I'm reading the wrong slide. Some people who are guessing 4. Well, let's see what it is. Oh, so we're getting several different guesses. Okay, so we're getting 2 and we're getting 4 as our answers. Well, let's try figuring this out. So this is equal to, well, let's divide. So 1,234 divided by 24. And so that's going to be 5. So that's 120, 34, 1. So 51, 24, 10. So remainder 10. So that's equal to the greatest common divisor of 10 and 24. And then, so once we've done that, then you repeat your process. So 24 and 10. So that's, that's just 2, 20, remainder 4. So that's equal to the greatest common divisor of 4 and 10, which is then going to be equal to the greatest common divisor of 2 and 4, which is going to be equal to 2. And I had one other example question to find the least common multiple. But of course, that's just the same process. Once you find the greatest common divisor, then you have to multiply it back through. So you should try this one out on your own time. But I should end class here. So thank you all very much. And I will see you guys on Monday.